All right. I wanted to make a video for you guys talking about the conservation of momentum. And just like how with the energy chapter we said EI equals EF, with momentum, we're going to be able to say that PI equals PF. And up to this point, we've used our formula for momentum, which is P equals mv, and impulse, which is J equals F times T. We've used these formulas combined by saying that delta P is equal to J. That MVF minus MVI is equal to F times T. And we call this the impulse momentum theorem. Now, this is good when you're interested in one object. Maybe a ball collides with the wall, and all you care about is what happens to the ball, the force on the ball, the mass of the ball times the velocity initial of the ball, the mass of the ball times the velocity final of the ball. But there's two objects in that collision. So another way of looking at collisions then would be using the conservation of momentum. Let me go ahead and rewrite that formula. PI equals PF. The way we deal with this then is we write this, if there's only two objects, we say that the momentum initial of object 1 plus the momentum initial of object 2 is equal to the momentum final of object 1 plus the momentum final of object 2. And those are just commas in there that I tried to use. And so what we're saying is all of the initial momentum added up should equal all the final momentum added up. And I think it's probably best to see how useful this is with an example problem. But we're going to utilize this when there's two objects in collisions. And it could be more than two objects. But we'll start with two objects because that's an easy way to see it. All right, so an example problem that shows this will be on this sheet, this review sheet, which I think I'm going to give to you on Schoology. And on the back of it, we're going to look right here at number 6. It talks about a 50 kilogram bicycle moving at 12 meters per second, contacts a 25 kilogram toy truck moving at 5 meters per second in the opposite direction. The toy truck's velocity increases to 15 meters per second. What's the velocity, final velocity of the bike? All right, so it does seem like there's a lot more going on with this problem, but there's something we can use with momentum problems which makes them a little bit easier and a little bit nicer. And that is we can think of them in terms of before and after. So we'll start with the before first, right? And so I'm going to do a drawing, and it says for the bicycle, and we'll have the bicycle moving to the right, and just arbitrarily picking a direction. It says it's moving at 12 meters per second. The mass of the bicycle, I'll call it MB, is equal to 50. All right, and then it says we have a toy truck, so try and draw that. The mass of the toy truck, call it MT, is equal to 25 kilograms. And the toy truck is going to be moving in the opposite direction. So it's going to have a VI of 5 meters per second, but since it's to the left, we're going to call that negative. All right, so we have something like that there for our before. And then obviously these two objects are going to collide, and then we can go ahead and draw the after. It says after the toy truck's velocity increases to 15 meters per second. Well, this toy truck isn't moving as fast. It doesn't have as much mass. So if it increases to 15, that's going to be 15 to the right. And it's not written totally clearly, but that's what that's saying. And then it says, what's the final velocity of the bike? So what we know then is that this toy truck, I'm going to go ahead and draw it there, is now moving to the right at a larger velocity of, we'll say, VF. And I should be probably calling this VIB and VIT. I guess that wouldn't hurt. Just so I keep these two clear on what they are. And then this will be VFT, right? The final velocity of the truck is equal to positive 15 because it's going to be to the right. So I made a decision here with this problem that I was going to call right positive and left negative. All right, that was something I decided from the get-go. Okay, so if that's true right there, then we can say the mass of the truck is still going to be the same, but the mass of the bicycle is still going to be the same, but what we want to know is what happens to this bicycle. Does it continue to move to the right? Does it get knocked back by the truck and move left? And that's really what the question is asking. And it's a good question, right? We don't know. We could see maybe both things happening, right? If this happened outside on the playground or something, or in real life, if there was a collision between a bicycle and a toy truck, you wouldn't necessarily know what happened until you tried it. So, all right then. So let's go ahead and plug this in our formula, which is right up here. But you notice here we have P written for each of these, and that here we have M and V. So what we're going to do then is we're going to take this formula, right? And I'm going to write it one more time, but specifically for this, specifically for this problem. So I'll show you what I mean here in a second. All right, so we're going to go ahead and say PI equals PF. And in the momentum initial of object 1, we'll call object 1 the bike. Just make a decision there. So we're going to have MB. So here we're going to have, we have to remember P equals MV. So I'll have the mass of the bike times the velocity of the bike initial, right? And we'll have, we'll add that to the mass of the truck times the velocity of the truck initial. And I know I wrote that differently in those two cases, but that's fine. It doesn't matter if the T or the I comes first. It's just, those are just descriptors. And this is the initial side. So what I'm trying to say is this right here, PI, is represented by these two quantities added together. The negative sign that is happening right here, we will put in right here when we put the negative 5 meters per second in right here. But we're always going to add the two momentums together. And then we're going to set that equal to the final momentum, which is going to be the mass of the bike times the velocity final of the bike, plus the mass of the truck times the velocity final of the truck. Kind of running out of room there. All right, so it's quite a long equation to write, right? It's pretty annoying. So what this is then, right? If I go back up here and rewrite this in a more generic way, maybe right here, right, is if I have room, maybe I do. Let me try. I'll write them here in pencil. Is that I have M1 times V1 or V1 initial plus M2 times V2 initial is equal to M1 times V1 final plus M2 times V2 final. So this is really the equation we're going to be using most of the time here to solve these problems, generically written for any problem, right? This is specifically for the bike and the truck, but generically written, it'll look like this. And that's what we'll end up using going forward. Sometimes the object will start at rest, and so maybe their velocity initial of one of these objects would be 0. Maybe at the end, one of the objects might not be moving. Its final velocity would be 0. So that can happen as well. All right, so let's come down here. Let's go ahead and plug in our numbers from over here. So the mass of the bike is 50 kilograms. The velocity initial of the bike is that positive 12 meters per second. We're going to go ahead and add that to the mass of the truck, which is 25 kilograms, times the velocity initial of the truck, which is here. We're going to go ahead and put that negative sign on, and that's super important. You can't forget that. The mass of the bike final is still 50. Velocity final of the bike, we don't know, so that's what we're going to solve for. We always got to have one variable that is unknown. Mass of the truck is 25 kilograms, and the velocity final of the truck is that positive 15. All right, and now we can go ahead and do a little math here. 5 times 12 is 60, so we can say that 50 times 12 is going to be 600. And signs are important here. So this is a positive 600. We're going to go ahead, 25 times negative 5 is going to be negative 125. I know there's a plus, a negative, so it's going to end up looking like this, right? And we're going to set that equal to 50 kilograms times VFB plus 25 times 15. Ooh, that one I better you get the calculator for. Maybe 375. I'm just guessing. Yeah, 375. All right, so something like that, right? So we'll go ahead and do the math over here. 600 minus 125 is 475. We're going to just go ahead and rewrite everything. Whoops, I think I forgot a parenthesis right there. Yep. And then we'll go ahead and subtract 375 from each side. So I think if we minus that 375 minus 375, we can go ahead and cancel there, and we're left with 100 over there. So I ran out of room here, so I'll come up here to the top maybe, see if I can fit it in right here. So I'll be left with 100 kilogram meters per second, and is equal to 50 kilogram meters per second times VFB. Divide both sides by 50. Obviously sending the units over there with it. Just getting a little lazy there, not writing that. I don't like those units. Oh, I see what I did wrong. So if I come back here, the units on this 50 are just kilograms. So I got to be careful there. All right, so right here, I do not have the meters per second there, and therefore I'm only dividing by 50 kilograms. All right, so when we cancel here, we can cancel 50s, cancel kgs, cancel kg. 100 divided by 50, this is going to be 2, so this is going to be 2 over 1. So we're going to go ahead and say that that answer then is 2 meters per second is the VFB. Paying attention here to the sign, right? That it's positive 2 meters per second. So therefore the bike is still moving in the same direction it was initially, which is to the right. So what we saw there then is if we look back, is that momentum was conserved. And you might say, well, how is that the case, right? Because if we go back and look at this, we're like, this object's moving left, and so therefore it has negative momentum. This object's moving right, and therefore it has positive momentum. And you might say, well, in the end, both of these objects, right, this is actually equal to positive 2, right? So it's moving to the right. Both of these objects are moving right. Well, what we're saying then is that there was initially, if we go back and look, there was initially positive momentum to the right. Like right here, that positive 475 was the total momentum initial of these two objects. I don't care that one of them was moving left, right? That because even though it was moving left, it had such a small mass that there was still an overwhelming amount of momentum directed to the right. So in the end, there still had to be 475 kilogram meters per second directed to the right. And if we go back and look at that, we can see that, right? Because here we had 375 of that 475, and then 50 times VFB. Well, what was VFB? Well, it was positive 2. So 50 times 2 is equal to 100, right? So we have positive 100 right there. So positive 100 plus 375 is 475 to the right, positive 475. And over here on this side, positive 475 to the right. Aha, so momentum is conserved, even though these objects are moving in two different directions initially, and they're both moving in the same direction finally. It's still 475 to the right initially in the before, and 475 to the right finally in the after. Okay, hopefully that makes sense. And you're seeing how this works. So this PI equals PF, we balance momentum this way. It becomes this formula, where we add up the two initial momentums, set it equal to the two final momentums, and it becomes this mess to look at. But this is what we're going to end up using, and that's how we solve these problems, paying special attention to the sign. Okay, let's do another problem. All right, this problem I got from I had a note guide, or I had a sample problem. I think it's in the textbook that I'm going to go ahead and do. Might have just been one I made up. I can't remember, but that's okay. It says a 76 kilogram boater initially at rest in a stationary 45 kilogram boat steps out of the boat and onto the dock. If the boater moves out of the boat with a velocity of 2.5 meters per second to the right, what is the final velocity of the boat? Okay, so let's go ahead and start with the drawing and see if we can make some sense of this. Okay, so what it's going to look like is this. So we got a boat here and some water, right? Try and draw a dock. Ugh. Okay. Something like that, right? Kind of looks like a dock. Sure. Okay. And and this person's going to step out of the boat. They, well, this will be our before drawing. And what we're going to see is that initially the person is at rest in a stationary boat. So I guess I should just draw the person just standing in the boat. Okay, so initial velocity of the person is going to equal 0. Initial velocity of the boat is also going to equal 0. And that's it. That's what I have for initial. Mass of the boat is going to equal 45. Mass of the person is going to equal 76 kilograms. All right, so very simple for the before drawing. After drawing, the person is going to move out of the boat. This is going to have to be a little more dynamic here. Oh, that looks bad. All right, they're stepping out of the boat, obviously, and their final velocity is going to be directed that way, VFP, which is going to equal 2.5 meters per second. We want to know what is VFB. Now, I think we can make a prediction here, right? This is like if you were on a skateboard and you stepped off the skateboard and went this way, which way would the skateboard go? And I think most of you would say, what? Go ahead and think about it for a second, make a prediction. I think most of you would say if you are going this way to the right, that the skateboard would go to the left. And so that's what we're thinking here with the boat, right? Seems to make sense. Let's go ahead and do the momentum balance and find out if we're right. All right, so PI equals PF. And we have that complicated formula to write out one more time, right? We'll add up the initial momentum. So initial momentum of the boat, we'll say the boat is the first object. I'll just pick one first. Mass of the boat times velocity initial of the boat. We're going to add that to the mass of the person times the velocity initial of the person. And we're going to set that equal to the mass of the boat times the velocity final of the boat plus the mass of the person times the velocity initial of the person. All right, and we can go ahead and plug some numbers in. Mass of the boat is 45. Velocity initial of the boat is 0. Mass of the person is 76. Velocity initial of the person is 0. Mass of the boat is 45. Velocity final of the boat, we want to know, plus the mass of the person, which is still 76, times the velocity initial of the person, which is, or I'm sorry, this should be final. All right, didn't catch that till just right then. Velocity final of the person, which is that 2.5 to the right, so this is going to be that positive 2.5 meters per second. All right, so if we look at this side, we can see, and you probably saw this already, that both of these are going to equal 0. That there was no momentum initially, right? With no velocity, you have no momentum initially. So on this side, we're just going to have 0 because 0 plus 0 is equal to 0. All right, we're going to multiply that by 45 times VFB. What's 76 times 2.5? I should probably get the calculator for that one. Looks like that is 190, if you can see that. All right, then we're going to go ahead and send this over to the other, or one of these over to the other side. I'm going to send the 190 over there. So I have to subtract 190, and I'll write the units this time. I know I didn't last time, from both sides. So we're going to end up getting negative 190 kg meters per second is equal to 45. Both of these cancel out. Is equal to 45 kg times VFB. So then I can go ahead and divide both sides by 45 kilograms. Cancel the 45, cancel the kg. Cancel the kg. 190 divided by 45, well, negative 190. Is equal to negative 4.2 repeating. So I'm going to go with negative 4.22. So we can say that VFB is equal to negative 4.22 meters per second. All right, and just as we predicted, the final velocity of the boat is to the negative, or in the negative direction. So that means that this is going to go to the left at negative 4.22 meters per second. So what we're seeing there then is that momentum is conserved. Now, why is that in this case? Well, we initially had 0 momentum, but for both objects, right? But finally, we have 2 objects moving, one moving faster to the left and one moving slower to the right. But why does that make sense that it's still 0? Right? I mean, why would the momentums balance, or the before and after momentums balance? Because the before was 0. So that means that the after was 0. It has to be 0. Last time, the before was mainly to the right at 475, and the after is also 475 to the right. So it's not that they have to cancel each other out per se, right? It's more that whatever the initial was, the final has to be, right? Because in this case, the momentum was largely to the right initially and largely to the right finally. So momentum is conserved. In this case, the momentum is 0 initially and finally has to still be 0. So does that work? Does that make sense? Well, I bet if you take negative 4.22 times, what was the mass of the boat? 45. You multiply those two together, that is the same answer as, but negative, as the mass of the person, which is the 76 times 2.5. And what would that equal? Well, 76 times 2.5 is 190, right? So what I'm saying then is that if this is 190 to the right, that this has to be 190 to the left. Is that true that negative 4.222 times 45 is 190? Yeah, you can see it just based on what's already there. Yeah, it is. So in this case, momentum is still conserved because we have 0 initial and we have 190 to the right and 190 to the left here from the boat, and so 0 final. All right, so here that's how we're seeing momentum conserved. Kind of 2 different ways there, but that's the idea, right? That during a collision, this is a collision, even just a person stepping off of a boat, that the momentum is conserved. All right, hopefully that helps. I think I'm going to do, my phone's kind of running low on batteries, so I'll do another video of problem 4 from the homework assignment to help out, and hope everything's going well. All right, let me know if there's any questions, and take care.